In today's video, we're going to concentrate on two of our special quadrilaterals, parallelograms and rectangles. So just as a quick reminder, let's go ahead and mark some of the properties that we talked about last lesson with these two quadrilaterals, and then we'll look at some examples that use these properties and have us solving for either missing side or angle, or just solving for a variable in the problem. So for parallelograms, our biggest ideas to start with are our opposite sides are parallel. They're also congruent to each other, and opposite angles are also congruent. So in our first parallelogram, let's go ahead and mark those. So don't forget, when you have parallel lines, we usually mark that as a pair of arrows or triangles. Or we have a pair here. And again, matching number of arrows or triangles on the lines that are parallel. Now, this doesn't mean that those are necessarily congruent unless we know either we've got both pairs are parallel, which means it's a parallelogram, or both pairs are congruent. So again, congruent we mark with dashes rather than the arrows. So keep an eye out for both of them. However, if you have one pair of sides that's both parallel and congruent, that's actually enough to prove that it is indeed a parallelogram. Okay, we also have the diagonals bisect each other and they create two congruent triangles. So let's look at our second diagram that has the diagonals drawn in. And so if the diagonals bisect each other, then that means along each diagonal, again going vertex to vertex, the pieces are going to be congruent. However, that doesn't mean that all four pieces of those diagonals are congruent to each other. In this parallelogram, we definitely have kind of from the top left to the bottom right, that diagonal is actually a little bit shorter than the other diagonal going from the bottom left to the top right. So be careful with parallelograms. Another extra piece that goes to this, if I know that my opposite sides are parallel and my diagonal is working like a transversal, I can also use a very specific pair of equal angles, specifically our alternate interior angles. Now these popped up a lot when we had our congruent triangles as well. Anytime we have parallel lines, that can be the case. So we could have this pair of angles being congruent, alternate interior angles. We could also have kind of the adjacent pair with those. And again, in each corner, two completely different sized angles. So we know that our corner angles are not getting bisected, but we do have the alternate interior angles. And we can do the same thing with the alternate pair. So we have, I'm going to use stars for this next pair. And how about a happy face for the remaining pair? And also too, because you'll notice that each opposite vertex, it's made up of the same two parts. Those opposite angles are still also congruent to each other. And then if we look at our congruent triangles, I actually have enough just based off of these marks to use the angle-side congruence theorem. So I do have multiple pairs or two pairs of congruent triangles, actually four pairs. We could have our small triangles that are left and right. Those are congruent to each other. The kind of obtuse triangles, top and bottom, or we could look at the triangles that are created by each diagonal, kind of the half of that parallelogram. All right, now let's look at our rectangles. So in rectangles, and let me change my color. So in rectangles, they have all the same properties as parallelograms. So we're not going to mark every single one of the things that we just marked, but we know that they're all true. Opposite angles are congruent and parallel, opposite angles are congruent. We could have diagonals bisecting each other, and we can have the multiple pairs of congruent triangles created. But we also have the extra two pieces that all of our vertex angles are right. So in other words, all of our corner angles are all right angles. And so we could actually divide the shape if we just drew one diagonal, for example, this one. We actually divide it into two congruent right triangles. So we could, if we wanted to, use all the rules from Unit 7 with our right triangles, our trigonometry, although we won't see that too much, Pythagorean theorem if we need to find a missing side. So all of those are fair game. If we look at our diagonals, well, the diagonals in a rectangle are congruent. We don't have the shape skewed like we did for a parallelogram. So That means if the diagonals themselves are congruent, then when we bisect them, when we cut each one of them in half, what's going to be true about the halves? Well, they're also going to be congruent. So if I had just two diagonals, so let's say in our top rectangle, I have my red diagonal and I have my green diagonal. Those are congruent to each other. But in that bottom shape where I have the two diagonals intersecting in the middle, actually, if they're all bisected, then that means every single one of these pieces is all congruent to each other. And so we have a whole bunch of isosceles triangles in our figure. And so again, we can use all the properties that we know about triangles to answer any of these questions. So first, let's look at some parallelogram problems. Here we go. So in example 1, we have parallelogram WXYZ. And let's start labeling the info as we read through. So segment XY is 15, so that's on the right-hand side. WX is 22, that's the top section. ZX is 32, that's actually the entire diagonal going through. And so I want to be specific that I'm labeling the entire diagonal, not just one section. We have WT, which is just one section inside, so that's just this piece. And then we get to angle. So actually, let's deal with our sides first. So looking at the 22, the top side of our parallelogram, well, what do we know about opposite sides of our parallelogram? They are indeed congruent. So the base is also 22. We can do the same thing with the 15. So 15 is also going to be labeling the left-hand side of the triangle, the parallelogram, WZ. Okay, then looking at our diagonal 32. Again, one of the things that we know, and we can see in that diagram right above, is that the diagonals bisect each other. So if the entire diagonal is 32, half that diagonal is going to be 18. 16. And so let's label each section. I'm actually going to change my color for this. Let's go to purple. So we'll have 16 and 16. And then looking at the 10 that we have, well, if segment WT is 10, then the other half of that diagonal also needs to be 10. And so let's go ahead and label out the sides that they're asking us to find the measures for. We have ZW, well, we already labeled that as 15. We have ZY, which we just labeled as 22. We have segment TX, which is kind of the top right piece of a diagonal, which we just labeled as 16. And we have segment WY. Now we don't have that segment labeled, but the two pieces of it, the WT and the TY put together, the 10 and the 10 means the entire diagonal has to be 20 degrees or 20 units. Alrighty, now let's look at our angle. So I'm going to turn over to blue for this. Alrighty, here we go. So we have angle WZY. So WZY, tracing your letters around, is actually making this bottom left corner. So the entire angle here is 62 degrees. Okay, we also know that WXT, again, trace your sides around, or trace through the points, the vertices. WXT is 27, so WXT, this little guy, the top portion of the top right angle, is 27 degrees. And we know that ZWT, so ZWT on the top left, it's the bottom portion, that's 77 degrees. So again, before we answer any questions about the angles, let's go ahead and label everything else we have in the diagram. So that big angle down in the bottom corner, the entire angle Z, is 62 degrees. And because we know that opposite angles have to be congruent, we know that the entire angle at the top right, so angle WXY, is also going to have to be 62 degrees. We know one portion of that is 27, so that means what does the remaining portion need to be? Just whatever 62 minus 27 is. So subtracting that out, we get 35 degrees. And so because that angle is split as a 27 and a 35, we can do the same split down on the bottom left, just in case. And so don't forget, we're using alternate interior angles, again, just like the ones that we have in the diagram right above in the purple. And so I actually need to flip-flop that. So my alternate interior angle to that 27 degrees up by the X is actually going to be the bottom portion of that bottom left angle, otherwise known as angle YZT. And then we can do 35 in the other portion. We can do exactly the same thing with the 77. So alternate interior angle is going to be down by the Y, the top portion. Technically, we could call that angle WYX. And again, we want to be very specific as we can to make sure that we have exactly the right location for that angle. So let's see what angles they're asking us for if we need to do any extra calculations. So here we go, TZY. So TZY, again, trace your letters through. TZY is actually looking at this green angle, which we are already labeled as 27 degrees. Okay, angle XYZ. So XYZ is this bottom angle. Yep, we're going to have to do a little bit more math. So here's the thing, we have a whole or two pairs of parallel lines on here. So all of our other properties are still going to be true. So if I know that I have parallel lines, for example, if I look at those bottom two parallel lines, I know this angle is 62 degrees. So what does that tell me? If I have two parallel lines, what does that tell me about the start angle? How would those two angles need to interact? Well, because they are same side or consecutive interior angles, I know they have to add to 180. So to figure out angle Y or angle XYZ, I need to do 180 minus the 62 minus the same side interior angle. And that leaves me with 118. Which makes sense, it's an obtuse angle, so we got an angle measure that's bigger than 90 degrees. Alrighty, and actually, while we're at it, now that I know that that large angle needs to be 118, I can find its adjacent angle. Again, I know those two angles have to add up to 118. If one of them is 77, how can I find the leftover? I can do 118, take away 77. So 118 minus 77, 41 degrees. 41 degrees. So let's see if that helps us out with anything else. We need angle XWT. So XWT is this guy right up next to the 77. I don't have that one labeled, but we just found it with the 41 degrees. Alternate interior angle with that bottom angle down at ZYT. And then angle XYT. So XYT, well, that's the blue 77 that we have labeled already. Again, be careful as you're doing these problems. You definitely want to make sure that you are taking your time and reviewing those. This is actually a fix to my first version of the video because I copied one of those angles wrong. So double check your work before you move on to the next problem. So example 2, we are told that we have a parallelogram PQRS and we need to figure out what angle R is. Well, let's see, angle R at the top right piece of our parallelogram is not labeled right now. So let's see what we can figure out with our other angles. Now, if this is a parallelogram, again, biggest word that's popping out at you when you say parallelogram is parallel. And so if I have parallel lines, for example, QR and PS would have to be parallel, they're opposite sides. Well, then what kind of angles do angle P and angle Q make? So don't forget, with our parallel lines, these guys are in these two spots. So they're not alternate interior angles, but what kind of pair of angles are they? Yeah, those are the consecutive or same side interior angles. And we know those can't be congruent, so the only other option is they add to 180. So let's go ahead and add the expressions and see where that gets us. So I'm going to do 8x minus 12 plus 3x plus 5 equals 180. And then I can go through and solve for x. So combine my like terms, I have 11x. Negative 12 plus 5 is a negative 7. and 180. So add a 7 to both sides will give us 187. And that actually divides out pretty nice. 187 divided by 11 gives us, excuse me, let me type that correctly, 17. So we haven't found R yet though. But what do you know that R has to be equal to? Well, if opposite angles in a parallelogram are congruent, he has to be congruent to angle P. So angle R equals angle P, which is 3x plus 5. And now we know our value for x, so we can just plug it in. So 3 times 17 plus 5. That's going to give me, see, 17 times 3, 51 plus 5, otherwise known as 56 degrees is our final answer. And that does look appropriate for the diagram. Again, diagrams are not always to scale, but they may give you a good idea as to whether you're on the right track with your answers. Alrighty, let's look at examples 3 and 4. So again, 2 parallelograms, and actually these are, let's see, let's keep going. So example 3, parallelograms, our angles are not quite exactly in the same spots, but we were given extra information. So in parallelogram JKLH, if angle KLH is 134 degrees, so let's place that. So KLH is this angle down here, and that's 134 degrees. Well, let's see here. That doesn't really get us all the way there yet, but what do we have with the 25 degrees and the 4x plus 9 degrees? Well, with where they're located doesn't really help me out unless I knew what angle J was, do we? Angle L and angle J have to be congruent. They're opposite angles. And now if I look at the big triangle on the top left, let me change over to red. Now I know all of the angles in that triangle, and all my angles have to add to 180. So 25 plus 134 plus 4x plus 9 equals 180. And all we need to do is solve for x, no plugging back in. So combine your like terms. We only have the 4x. And then we have to combine all the rest of the numbers. So 25 plus 134 plus 9 gives me 168. Subtract that from 180. We get, let's see, 180 minus 168. We get a 12, so x is actually only equal to 3. Alrighty, example 4. Again, another parallelogram. We know that AC is 8x minus 14. That's one of our diagonals. EC is this piece. Wait a second. What do we know what happens to each one of our diagonals in a parallelogram? When they intersect each other, they bisect each other. So that means EC is half of our diagonal AC. So if that's the case, there's 2 ways we could do this. We could take half of segment AC, or we could just take EC and divide or multiply it times 2. So I know 2 times EC would be the same thing as AC. So let's approach it like that. So 2 times my EC expression, 2x plus 11, equals AC, which is 8x minus 14. Distribute out your 2. For a 4x plus 22, and then solve for x. Subtract a 4x from both sides gives me a 4x on the right. Add 14 to both sides, that's going to give me a 36. And again, another problem that divides out very nicely. 9 is my x. And so notice I didn't label my diagram with the expressions, but I still marked up my diagram to understand how the pieces related to each other. Always do something with a diagram. Draw it out, or if you have a printer, you can always print out your notes and draw on the diagrams as I do. Okay, last example on parallelograms. So these 2 angles, what spots are they in? They're both inside our parallel lines, but one's on the top, one's on the bottom. So they are actually alternate interior angles, which means in this parallelogram, those angles have to be congruent. So let's go ahead and set our expressions equal. So we have 2x squared plus x equals 3x squared minus 20. Now, this looks a lot like one of those practice problems we did at the end of factoring. We are going to have to solve by factoring on this problem. So we need to move everything over on one side of the equal sign. I'm going to move everything towards that 3x squared to keep my x squared term positive. So that means I'm going to subtract 2x squared from both sides, which would leave me with just a single x squared, and then subtract x from both sides. And I'm going to put it right in the middle, in between the x squared and the negative 20. Because again, when we factor, we like seeing things that are lined up x squared, x, and numbered. And so now this is a lot more straightforward to factor. Again, if you need to use box method, go for it. See, we don't have any weird coefficients to look for at that numerator or the leading coefficient, which is just a 1. So all I need to do is brainstorm on the 20. What kind of factors break out from the 20, but still add together to make a negative 1? Well, I could do a negative 5 and a positive 4. So filling in my box, I have x squared and negative 20. And then I have a negative 5x and a positive 4x. And again, the order doesn't matter with where you fill it in. You're still going to have a negative that's in common either one row or one column. So our factors will come out to a common x from the first row, a common negative 5, from the first column and second column. First row, we just have an x in common. Second row, we have a 4 in common. The negative was already taken out, so that's my positive factor. So 0 equals x minus 5 and x plus 4. So then set each factor equal to 0. So x minus 5 equals 0, which means x equals 0. And x plus 4 equals 0, which means x could also be, my first one is not 0. What did I do? X minus 5 equals 0. I have to add a 5 to make x equals 5. And in the second equation, x plus 4, I need to subtract a 4, so x equals negative 4. And so we want to double check, could both of these work? It's this negative answer that I'm worried about, because we can't have any negative lengths or negative angle measures in geometry. So if I plug that back in, let's see, if I plug that into 2x squared plus negative 4, well, any value that's negative that we square, we always get a positive answer. So this is really 2 times 16 minus 4, otherwise known as 32 minus 4, definitely a positive number. That gives us 28. So I'm going to try that with a 3x squared. So 3 times negative 4 squared minus 20. So 3 times 16 minus 20. 16 times 3 is 48. 48 minus 20 definitely gives us a smaller number of 28. So I've done two things at one go. I've checked to make sure that that negative answer still works. And I've also double checked that my math must have worked because I got the same measures out for both of these. So two solutions, negative 4 and 5. All right, now might be a good time to take a break in the video, do a quick lap around the room, and then come back and look at the rectangle problems.